finding maximum bending moments, we need to find the points of maximum displacement. The displacements that we're interested in are the downward vertical displacements, which in this model are in the y direction. We should again begin with a diagram under Results, Diagrams, Deflected Shape. If we choose Apply, we see a deflected shape. The deflected shape shows us visually where the maximum displacements are, and we can then go retrieve numerical values of those displacements. For example, in the bottom of the three bridges, the maximum downward displacement occurs at either this bottom node or this top node. To get numerical values of the displacements, we go to Results, Node Displacements, and select the node that we're interested in. We see then that the y direction displacement in this case is 1.38 inches, because we've used inches to define the model, and it's negative to indicate that it's downward. If we click on this node, we see that the displacement here is negative 1.377 inches. The displacement is slightly larger at node 19 at the bottom than at the top. So this value, 1.38 inches downward, is the point of maximum downward displacement in bridge number 3. You'll need to find the point of maximum displacement for the other two bridges. After finding displacements, our job is to figure out what the weight of each of these bridges is. We've assigned a density to the steel material that's used to build these models, and turned on gravity so that the self-weight of the structures is automatically included. We can therefore find the weight of the bridges by finding the total upward vertical reactions and subtracting out the applied loads, which, as this problem is defined, are 30 kips total across the span. Let's look at bridge number 1. If we go to Results, Node Reactions, and select node 1, we're told at the bottom of the screen that Fy, the vertical or y direction reaction, is 15.65 kips in this case. Over at node 4, because of symmetry, the vertical reaction is the same, 15.65 kips. That means that the total upward reaction is twice 15.65, which is 31.3 kips. Because we've applied a total downward force of 30 kips to the bridge, 15 kips at this node and 15 kips at this node, the remaining upward vertical reaction that accounts for the self-weight of the structure is 1.3 kips in this case, meaning that our bridge weighs 1,300 pounds. You should investigate reactions on the other bridges to determine their self-weight. Once you've completed all of these activities, you now have enough data to make meaningful comparisons between the performance of these three bridges.